Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome you in lecture 2. Student, basically we don't complete lecture for fun of this example, okay? So let us revisit again the the example, okay? So we start this example, and this is a design example. Clear? We explain this example, okay? We explain basically bracing and unbracing structure, and we did this example up to this point. Clear? So before start this example, I want to show you some interesting videos, okay, which is related to buckling, or you can say lateral torsional buckling, and you can say sub bracing and unbracing length, okay? So let me show you. Let's say we will start this way. Clear? So here, students, you will see basically okay. So students, you can see here we have basically a beam structure, okay? The web, however, prevents the flange. So this is very important that you must know that we have basically this one is basically this portion is web. Clear? This is almost in a T section. Clear? But if we have an I section, let's say this one, so this is web and this is flange, okay? So web basically restraining the buckling. Clear? The lateral torsional buckling. Almost this is the flange which buckles, okay? So here this point is basically explained in this video. Clear? So let us this is a kind of lateral torsional buckling, but this is a column when it's converted into a beam, okay? The tension flange. This is I beam, okay? And you see here, this is the graph, okay? I will explain this graph. Clear? Clear? This is an elastic zone and this is plastic zone. Clear? We have to design basically in these two time zone, okay? What is elastic lateral torsional buckling? Let's see. Load is applied, okay, and you see this is how we call a lateral torsional buckling, okay? This. Clear? This is very interesting, student. This is basically lateral torsional buckling, that the beam is basically you see here, these are the initial axes of the beam, and now these are the buckle axes. So this lateral deflection is basically lateral torsional buckling. You see here, although the beam is not bending, the beam is move in basically move in lateral direction. So therefore it is called lateral torsional buckling. One thing is lateral the one is twisting of the beam. You can say torsional buckling. I will show you the torsional buckling as well, but this is basically lateral torsional buckling. And how we prevent this? By restraining the beam in horizontal direction. We provide basically restraints in horizontal direction, and then those are basically called bracing, okay? And if we brace this beam in throughout its length, like the one which I will explain you, that the upper portion is basically insert of the beam insert into a concrete, so that provides a continuous bracing, and in that case basically your LB equals to 0, okay? That is your unsupported and unsupported length. Your unsupported length equals to 0. But if you don't provide basically the continuous bracing and you provide intermittent bracing, I will show you this intermittent bracing, then your LB will be this length, okay? So this is very important when you are designing a beam. Clear? So you people must know about the lateral torsional buckle. So this is, you can see the buckle beam. So this type of buckling is elastic. When the load is removed, the member returns to its original shape. Yes, when the load is removed, the beam is come back to its. See, this is how. Clear? Now, this is the graph, and this one is basically important. Okay, this is the plastic zone. This is the elastic zone. We have to design basically in these two regions. Almost we're trying to design the beam because the capacity of the beam is the highest in this zone, then the lowest in this zone, while there is the intermediate one. So always we try to basically to design this in this zone. But if you want to design the beam in this zone, you have to provide basically a your bracing. Okay, so shorter beams that are not laterally supported may experience inelastic lateral. There is inelastic lateral torsion buckling. Okay, so let's see. A larger capacity does not allow enough deflection to prevent the residual stresses. Okay, so let's see this one. Beam is loaded. Okay, this type of buckling is inelastic. The non-elastic portion of the deformation remains when the load is removed. Yes, this is the difference. Okay, you see here that the beam does not come back to its original position. Elastic zone, the beam come back to its original position. So this is how we basically see. So this is these zones. Okay, this is an elastic zone, and that is the plastic zone. Clear? So it is very important. Let me show you another video. Not this one. Material lab. Okay, this test, see this test. Okay, so you see here basically a flat girder. Okay, you see here this is the beam. Okay, and the load is applied to the 2 points. Okay, now you see these are there, the load is applied. Okay, and basically okay, you see here that basically the load are applied here. Clear? The loads are applied here. Okay, there you are loading. Clear? And you see the lateral torsional buckling. You see this. Okay, this is not bending. Okay, bending is basically the beam in vertical direction, but this is in horizontal direction. Clear? You see the deflection of the beam from its basically from its initial axis in horizontal direction. This is your lateral torsional buckling, and the beam twists like in this direction, bend like in this direction. So to prevent this one, we need to apply a force overhead to bring back the beam into its original position. So for that, we provide lateral support to the beam. Clear? Lateral support to the beam, and that basically divides the beam into two different or separate portions. Clear? So this you can see here. Okay. So this was also where look this video. Clear? You see here the load is applied to the midpoint. The beam is simply supported, and you see the load is applied. Clear? You see, look how the beam basically buckled in horizontal direction. So see, this is an example, very important. Okay, this is how we say this is lateral torsion buckling. Clear? And I want to show you another video that is very important. Okay, here you see here what is a restrained structure or an unrestrained. Basically unrestrained structure basically which you do not provide any horizontal support at intermediate points. So you see this is the main beam basically, here, this is your main beam and this is your secondary beam. Okay, so this secondary beam basically prevent the horizontal or buckling, lateral torsional buckling of that beam. So it's increasing the capacity of that main beam, this secondary beam. Okay, so if you don't provide, it will lose in its maximum capacity. So sides way basically provide it prevent the side. So this way basically we provide what we did basically we the top portion, almost it was important, almost the top portion of the beam, this plain portion of the beam is basically buckled, although tension portion do not buckle. Okay, so therefore we basically we insert the flange, the top compression flange into concrete that provide a continuous support to the beam to prevent its lateral torsional buckling. Clear? So that is the advantage of basically how we can increase the beam capacity. So these are lateral bracing basically provided. Yes, this is very important. You see here lateral bracing, so to prevent the beam in lateral direction. This one we basically conceal the beam into concrete to prevent its lateral torsional buckling. Okay, so lateral restraints. Okay, these lateral restraints are provided to the column and the beam as well to prevent it from lateral torsional buckling. You see these are the these failures. Okay, these are basically failures of beam. This is local torsional buckling and global buckling, one thing you can say. This is basically slenderness effect, and this is very important to note down that you see the flange is buckled. Basically this give birth to the idea of compact section, slender section. Okay, your beam is not slender basically, your beam is slender. So this kind of local buckling is occurred. Local buckling means the web is buckled out, or you can say the flange is buckled out. Now although the whole member do not fail, some part of the beam you can see here, as well as you can see this is the bend like. Okay, so that is a lateral torsional buckling. Clear? And you see here, this is very important. Okay, you must notice this kind of failure. This is basically local torsional buckling of flange. Okay, because only this is not a global failure. This is a local failure, you can say, because only this flange is basically bent out. Okay, you see here the flange is buckled. Okay, the web is not buckled. So this is local flange buckling. To prevent this, the section should be compact. Now what is compact section? We explain this in this example as well. Okay, so this is how we can define local torsional buckling and how to prevent these local torsional buckling. I will show you more other videos. So let us come back to the topic. Okay, where we have to stop and complete the example. So this is a design example. Clear? So we stop here. Okay, whenever you want to design a beam, okay, you have to find out your modulus. Okay, plastic section modulus, that is plastic section. Okay, plastic section, or you can say your z-axis. Okay, your elastic section modulus and your plastic section modulus. So this is your plastic section modulus, zx. Now as it is already given, you have to select W10 section. Okay, but the lightest W10 section. So you calculate your zx. Now coming back to the table and search such a section which is W10, but whose zx close to this value, more than this one but close one. Okay, so that basically the design process of the beam. Now we are going toward the manual, okay, and we search such section whose ZX is close to this one. So let us coming back to the manual, okay, and we choose the value, okay. So as we have W section, so clicking this one, this is a W section, starts 144 and going to W10, okay. So let me drag W10 section, clear. So this is your W10, clear. And here you can see basically this is 68, okay, this is 68. You see the properties, the various properties, the gross area of this section W68, the dip, the whole dip, the thickness of the web, okay, the thickness of the flange and the width, okay, and these are different parameters. You come to here, this section is continued, okay, and the rest of the properties are there, okay. So here you can see nominal weight of the section, that is 60, okay, and you can see compact section criteria. These are, we will use these in our coming lectures, okay, as well. What we need this ZX, clear. So as we our calculated ZX is basically 80, okay, and we have to select the lightest W10 section, okay. So we have W10. Now we search which W10 section give us close value to this 80. So you see here we have basically W10 112 whose ZX and 100. We search these value, which one is close, okay. So here you see WZX 147, 130, 113. So this value, okay, this value is close, clear, because the 74 one is less than 80. So that's why we reject this one and we select this one. This one we can also select this one. Almost select such a section which is a little bit higher than the calculated one, because we have to check other check, okay. So that's why you can select basically 97, okay, this one 97, a 77, okay, as well. So always select 3 to 2 sections, okay, and check them one by one, clear. So we choose this section, basically this one. We choose this one. This, okay, 77 or 68, okay. So we can use these both, either 68 or either 77. So we choose basically W10 68 section whose ZX is basically 85.3. Now we calculate its capacity, whether its capacity is more than the design capacity. So pi b MP, okay, pi b is 0.9 and pi b MP is equals to ZX into Fy. So ZX is 85.3 and Fy is 50, divided by 12 to convert it into feet. So you see 320 kif feet, which is more than 300. Our section is okay. Note, if you are using 14 edition of the section, or if you are using AISC manual, okay, which is this one, so how you can design this manual is a little bit, you can say this is a modified, okay. This is you can quickly design the section by using this section, because this is a little bit easier, okay, how we can design, okay. So let me use this manual as well, that how we can design if we don't have LRFD manual, okay. So as we calculated the movement capacity, that is 300. So you need to basically when you are using AISC manual, okay, so you need to our topic is basically design a flexure member, that is chapter 3. We are directly go to design a flexure member, that is chapter 3, okay, chapter 3, this one, clear. And this section is basically 3. These are composite section, okay. So you have to come basically the beam section, clear, this one. Now so you see here W24, we have to select a W10 section, clear. So here you can see W10 sections. You see the beauty of this AIC manual, that it gave you directly. Okay, so here we have W10 section. So W1026, here you see the design capacity. Okay, the design capacity pi b MP. Although we have different properties, but you see here we have to search the blue one, because these are LRFD. Okay, we don't care about ASD, because we don't design as an ASD, we design as an LRFD. Okay, so that's why pi b MP, the design capacity, which is in kef feet. Okay, so we design the capacity that is 300 kef feet. Clear? So let me search the section whose capacity is basically more than 300. Okay, W10 section, such a W10 section whose design capacity is more than basically 300. Clear? So let me choose 380. No, we have to choose W10 section. Okay, so basically here, okay, you see with 5 MB 320 from table 3.2, from table 3.2. Okay, so this is table 319. Okay, we have to go back to W10 section. Okay, that is table 3.2. Okay, so table 3.2, here, this one. Basically, no, this not this one. Okay, not this one. Table 3.2. That is basically because we are designing on the basis of Z. Okay, ZX. That's why that is basically table 3.2 is basically ZX table. Clear? So we are going back to table 3.2. Let's see. This is section 3, table 3.3. This is ZX table. So basically this is ZX table, because we calculate ZX. Clear? So although we search it in because we have to choose basically in AIC manual, we have to find out ZX. Okay, and the capacity which is more than 300. So let us see. These are the properties. You can see here this we need to search out this one. Clear? We need to search this one. Clear? So this 5B MPX. Okay, and this blue one, these blue one values. So these are the sections. Clear? We have to choose W10 section. So dragging downward and search W10 section. Okay, so here W10 112, it gives us a capacity of 551. Okay, this is more than 300, so that's why this is W1060 and W60 1066 68. This one give you 320. Although we can use 320. Okay, 320. W1068. If we search W1060, it gives us 280. So although there are different sections, other different sections, this one W77 gives us 360, which is more than 300. So this one will be a conservative value, and this will be an appropriate and economical value. You can say that it is close to 300 value. Okay, so we pick this section, and this one will be our required section, which is the most latest one. Okay, noting that we are using CB is equal to 1.0. We did this inshallah in coming lecture, in coming video as well. So this is how this end this example, that how to find a lattice section. Okay, and this is a design example. Okay, you see the procedure, and that how we can find the most lattice suitable section by using both, as well as LRFD section, LRFD manual, as well as AISC manual. If you have LRFD manual, I show the design procedure that you need to find out the ZX, you need to calculate ZX, then going back to the table and find out, okay, find out the such a section whose ZX is more than the calculated one, and then recalculate the capacity whether it is more than the, the required capacity. If you are using AIC manual, the procedure is simple. You need to find out the movement capacity, the movement which is the applied load, applied movement, and coming back to the ZX table in AIC manual, and you find out the section whose capacity is more than your calculated capacity, that is 300. So by using AIC manual, the procedure is simple, but by using LRFD manual, you have to do some theoretical calculation. Although this is this the book which I use. Okay, a very important information I want to share with you people, that this is the WSC GUI book. Okay, and a very you can say very important book for steel structure. Okay, it is a very informative book. Okay, it's instruction manual, you can search out, it will available on Google. Okay, this is 5th edition and William T. Sijui. Okay, very important. Okay, and very informative book. Okay, so basically the beams topic, this topic. Okay, so this ends up this example. See you inshallah in next lecture. That is lecture number 3. Okay, we did another example, that is determine if a W10-12 with a yield stress of 50 satisfy the compact section criteria, also determine its design flexion capacity. So it is a more advanced topic. Okay, compact section criteria, what are those criteria, and what is compact section, non-compact section. Okay, so we did this example inshallah in lecture 3. Until you have any question, please share